your ultimate goal is, can you write a story that has all these vocabulary words in it that tells somebody, I know how a candle works. I know the science of a candle. Yes, we got lots of seats up a little closer. All right, you ready? I will read the first 3 paragraphs, and then we'll have volunteers to read some others. So get ready, clear your throat, get ready to read, okay? The person who wrote this article, even though it was 1978, I remember watching him in some other science videos. He was a physics professor at MIT. Now, I'm not sure you know what MIT is. Do you know what that stands for? Massachusetts Institute of Technology. They have one in California, CIT. And I can tell you right now, if you thought it was hard to get into NC State or UNC, you think it's hard to get in Duke, try to get into MIT. MIT is primo. They're looking for somebody without, not just good grades. They might pick somebody who didn't have grades that are that great. They're looking for somebody who can really solve problems. Sometimes the federal government goes to MIT and says, we have this complex problem. Can you help us solve it? It could be electrical things. It could be weaponry. It could be anything. Economics. But MIT, anyway, so this guy must not be a slough-off, but he actually, the way he writes, you can understand him. So I'm going to help you understand him. It's in a magazine called Scientific American. Believe it or not, you can buy these at a grocery store who sells all kinds of, at a bookstore. You can go to a bookstore and buy Sports Illustrated, can't you? Well, you can buy Scientific American. Anyway, he wrote an article called The Amateur Scientist, and it's for people who said, hey, I'd like to try something like this, and that's what he's all about. I grew up with candles. They provided the illumination that held back the night in the midst of a big Texas storm. I mostly remember lying in bed before going to sleep, hypnotized by the flame, and wondered how the candle burned. I had seen other things burn, but they usually did not so fast. They didn't burn so fast. The candle burned so slowly that the wick lasted all night, even for 2 nights. Think about that. He's young, and he remembers when they lost power and they had candles, he had questions in his mind. Is that thing burning? You say, yeah, it's burning. Are you burning like other things? I burned paper before. Is that what it's like? I burned a piece of wood. Is it like that? He wants to know what makes it burn differently. Other features of the candle intrigued me almost as much. Why was the candle made of wax rather than some other material? Why was most of the flame yellow and a small region of the base blue? Why was there a dark inner cone between the wick and the yellow part of the flame? Why did some candles smoke? Others burn nicely and others flicker weakly. Finally, why was it that soot came from a smoky candle? Why was it black, whereas the white vapor came from a candle that had just been blown out? These are all old questions, and surely some of them have old answers. The fact remains that several of them, this is shocking to me, the fact remains several of these questions have yet to be answered with any certainty. What? Still? In this piece, I will describe to you how to make your own candles and how you might explore the physics and chemistry of a burning candle. Answers to some of these basic questions will emerge. In part 1, I shall be retracing the path of investigation followed by Michael Faraday, who was fascinated by both the simplicity and the complexity of the candle flames. Pretty good intro, huh? I got me interested. All right, I'd like somebody else to read the first 2 paragraphs. Thank you.
In addition to the paraffin from which my grandmother made her candles, many other materials have been employed. Tallow, stearin,
Spermaceti
from the sperm whale, and beeswax. Today you can buy paraffin in a grocery store or a hobby shop. Often it is already mixed with stearic acid to raise the melting point of the paraffin and therefore provide a stronger and slower burning candle. Wicks are also readily available. They are commonly made of plaited cotton yarn that has been
mordanted,
picked in a substance that inhibits smoking.
pickled.
The treatment is necessary because normal cotton would
composition. All right, so we got to back up. And I don't want to read this and say, well, I'm not sure what they said. So what we do is we take it apart. We try to dissect it and figure out what they're saying. One of the first things they said is the word paraffin. What do you think about that word? What's paraffin? It is. Paraffin is a wax. As a matter of fact, there are many kinds of wax, many. The one that most candles are made of is this kind. I'm not saying yours was, but most candles are this kind. And so paraffin is a wax. Now, a wax is an organic compound. Now, the word organic, until about 20 years ago, the word organic always meant carbon compound. But your generation, what do you know the word organic to mean? If you go to a store and buy organic cucumbers, what does that mean? Every cucumber is organic, but what does it mean in a store? They don't use pesticides.
And they're usually also not genetically modified.
No GMOs, no genetically modified organisms, right? And so for you, the word organic means something completely different than meat. And that's why it costs more money for your organic food, because they don't use pesticides and they try to not put chemicals on them. But the word organic in chemistry means a carbon compound. Now, I looked up paraffin, and the kind of paraffin they use for most waxes is this one, C25H52. Now, do you understand this is a chemical formula? Have you had this in middle school? Like H2O is a formula? This is a formula for a type of wax called paraffin. And notice that it's organic. It's a carbon compound, isn't it? And also notice that it only contains two elements. What are the two elements? And there's another word for you. Wax is a hydrocarbon. What does that mean? It only contains what? Hydrogen and carbon. Now, hydrocarbons all have many things in common. The stuff on the gasoline in your car, the gasoline in your car is a hydrocarbon. And the gasoline's a mixture of different carbon compounds, carbon and hydrogen. All hydrocarbons are fuels. All of them are fuels, meaning that they all can burn. They all can burn. Now, so that's the first word you saw was the word paraffin. And then they use the word burn. Okay, let's talk about that. What does burning mean in chemistry? And burning in chemistry means that you're combining in a chemical reaction with oxygen. Got that? So if you combine with oxygen in a chemical reaction, it's called burning. You can burn a metal. Got it? And you could burn paper. Now, what is it? Where does the candle find its oxygen? How does it combine with oxygen when the candle itself does not contain any oxygen? What?
The air.
Yes. Now, do you know a lot of people, they think this is oxygen? It's not, it's air. Got that? Now, what percent of air do you think is oxygen? Like 90%? 100?
2%.
How much?
About 2% is my guess.
We need more than 2, but yeah, there it is right there. So anyway, if you look up some books, they'll say that either 78 or 79, close to 80% of the air is stuff you don't even use. It's called nitrogen. You breathe in nitrogen, you breathe out nitrogen. In, out. In, out. It didn't do anything. But about 20% of every breath you need. And that candle needed that too. If you were to burn the candle in 100% oxygen, it would be tremendously brighter and the candle would burn way faster. And God was pretty smart. He said, I could put that whole atmosphere of the earth on oxygen. I could make it 100% oxygen, couldn't I? But I'll tell you one thing, you wouldn't need a fire department. Why not? It'd be gone. You aren't putting any fire out. 100% oxygen, it'll be so hot and burn so fast, you'd never get there in time. So it's pretty neat how that works. At 20% oxygen, that's what your candle looks like, right? Now, are you okay with that, the composition of air? And I know you can look up some other things. They'll say, 1/2 of 1% this, and you can look up some little things like that. All right, let's go on down now. Then they use this other chemical called stearin. Now, I didn't look up stearin. I don't have to know that, but what was the purpose of adding stearin to the paraffin? What do you think? What do you underline? Yes, Carter.
It raises the melting point of the plastic.
Raise the melting point. Why would you want to do that? Why do you want to raise the melting point?
So it'll burn longer?
Yes. You're on fire today. Candle. And why would you want it to last longer?
Get more use out of it.
That's right. Do you think that at one time when people made their own candles, like on the farm, you get some animal fat, make your own candles, do you think they lasted very long? Not really. But you know what? I'll make some more. But do you think maybe when people started living in cities, everybody wanted to make their own candles? They said, I'm good at making wheels. I'm not good at making candles, but I'll give you one of my wheels for 100 of your candles. How about that? I'll do that. So then people started making candles and said, I'm going to make money off this. Do you think maybe? I don't know. I'll even give you extra credit if you find out. Who was the first person to put stearin in candles? Where'd you come up with that? All of a sudden he said, I'm going to put something else with the paraffin. And it'll last longer. And guess what? What if you're a company who makes the old-fashioned candles and they cost a penny a piece back then? And then this new company comes up with one and now it has stearin. These last for 3 hours. These last for 2.5 days. 1 cent, 2 cents. Think about that. I'm buying a 2-cent one, right? It's going to last for 3 days. Now, what company is going to go out of business? This one. So at some time, they started putting stearin in candles, and more people bought it. The next thing you mentioned was, it's down here, the wicks. Why don't you just put a single strand of string in there? Why not? Why does it have to be braided? Did you guys notice that, your wick? Did you notice how the strings were intertwined? Did you notice that? And then, okay, so the first people to make candles, whoever made string, whoever, could weave that string in there. There must be some kind of a machine that made the little fibers go, and twist them. And that was nice, but then when did this happen? Somebody said, I'm going to chemically treat that wick. I'm going to pickle it. I'm going to mordan it. What? Why would you do that? Look what happens. Is anybody in this room, so far of the 2 classes I've asked, at least one person has done something in their house called pickling? Has anybody has they done any pickling at your house? You have?
Yeah.
What'd you pickle?
They're just called, I made them with my grandparents.
Are they vegetables?
They were pickles.
Egg? Oh, you made pickles.
Yeah.
Okay.
They were special ones though.
Did you know you take little cucumbers and you put them in these chemicals and then you put them in the pickle juice and they become pickles? A lot of people don't understand that pickles are cucumbers. They've been pickled. And some people have pickled eggs, pickled beets. Anybody ever done any of those? You have? Okay, so there's a chemical process there. You know what? Who in the world thought about this? Pickle the wick. What are you talking about? And let's read on. What did it say happened here? It did what? If you pickle the wick, guess what happened? What's that say? You mean before that? When you bought a candle, what happened? Lots of what? Black smoke. Well, that's the way it is. You want a candle, you get the black smoke with it, don't you? What do you think now? 2 cents a piece? 2 cents a piece. Didn't cost me that much to pickle the wick. Who's going to go out of business? The smoker. The guy with the smoky candles, right? All right, let's go on down. Oh, I tell you what, before we turn the page, let's go ahead and here's some other things they discovered. Everybody in this room should have noticed there were 3 distinct zones in the flame. Is that correct? Okay, we're going to read about those later. This one, the yellow part, is called the luminous zone. And what does the word luminate or illuminate mean? To illuminate or luminous. What's that mean? Gives off light, doesn't it? What was on Beauty and the Beast, what was the name of the person who used to be a candlestick of the candle? Lumiere. Lumiere, candlestick, right? The light giver. All right, anyway, let's take a look. We have the luminous zone, and then we had the dark zone. I like that name, the dark zone. And then we had the reaction zone, which looked blue. And the blue area is called the reaction zone. We're going to read about those later, but did everybody, in your observation, did everybody write down they thought there were 3 distinct parts of the flame or not? Uh-oh, not everybody's doing this. Everybody noticed the yellow part, right? Did you notice the black part, the dark part? Did you notice any blue? That's 3. Who actually wrote down there were 3 different parts of the flame? Ah, okay. Nobody? You just thought there were 2? You didn't think, okay. Now, you didn't have the equipment, but I'm going to tell you how to memorize these. It's not that hard. At the top of the wick, if you use a nice, not a regular thermometers won't work. This will break a regular thermometer. I remember, how old was I? 10 years old? And they had a little thermometer that they used to give out calendars, and they had a little thermometer on. You put the calendar up and a little red thermometer, you know. And I remember taking an old thermometer and the old one off the calendar, and I said, I wanted to know what happened. So I got some matches, all right? I got some matches. I struck the match, and I put it under the bottom of the thing, just like that. In about a tenth of a second, boom, it blew the end of that thermometer off, and the red stuff went everywhere. Regular thermometers would never be able to handle the heat of a match, let alone a candle. You get that? So they have special thermometers that are made out of 2 different kinds of metals. And they're called thermocouples, and they actually can read a different amount of electricity is produced, and they can tell you what temperature that is. By the way, I Googled this, and 600 Celsius is about a little over 1,000 degrees. It's about 1,100 degrees Fahrenheit. If you're wondering how hot that was, that's pretty hot, isn't it? All right, take a look. At the top of the wick, 600. Right above the wick, right above the wick, 800. At the top of the dark zone, 1,000. And in the yellow zone, about 1,200. So if you want to try to remember that, I have one picture like this on the test. 600. Right above the wick, 800. 1,000, 1,200. But surprisingly, I would have certainly thought this would have been the hottest zone. All right, but it's not. Where is it? And it's along about where the top of the blue area ends. And this is right here around 1,400 degrees. And we'll talk about that later. Why is that the hottest part of the flame? All right, let's move on. Now, let's go. I'm going to read the next person reading, they're going to read this paragraph and this paragraph. We're going to skip this one, okay? You don't need that one. So read this one and this one. All right, who feel like reading? Thank you.
Making a candle is not hard. I was shown how by Liz Hennep of Cleveland, but you will find similar procedures and more details in the many books on making candles. Set up a double boiler so that water is boiling in the bottom part and paraffin is heating at the top part. Monitor the temperature of the paraffin with a wax or candy thermometer. If the paraffin has not already been mixed with stearine for strengthening, it will melt in the temperature range from 48 to 74 degrees Celsius. If the stearine has not been included, an adding amount equal to about 5% of the volume of the paraffin. The stearine raises the melting point and will prevent the candles from burning too fast. Church candles are often pure stearine. Do not overheat your paraffin in the boiler and do not expose it directly to an open flame. If the paraffin should catch fire, dose it not with water but with baking soda. The successful burning of your candle will depend in part on the proper selection of the wick. Too wide a wick will result in a smoky flame. Too narrow of a wick will yield a weak flame that may die out. A rough rule of thumb is that the wick should be chosen according to the diameter of the candle. If the diameter is from 1 to 3 inches, use 15 ply wicks. For 4-inch or small taper candles, use 24 ply wicks, and for larger candles, use 30 ply wicks.
Now, you're not making a candle, But did you know that when people make candles, they actually have to decide what kind of wick goes in there? And you say, what? That wouldn't matter. Yeah. If you put a little tiny wick in there, what's going to happen?
It'll burn faster.
Very weak flame may even go out on its own, right? What if it's too big of a wick?
Also might put stuff in
Lots of smoke, right? Lots of smoke. And I think about that. Why is that? Let's go back over here. Double boiler. Why do you need a double boiler? You did not know how dangerous the candle lab is. I do. That's why I did all those safety things. You get that? Let's say you want to go home and make your own candle. And you go to the hobby store, get a block of paraffin. You go home. Let's say you have a gas stove. You get a pan, you throw it in there, and turn the gas stove on. And you wait and wait and start to melt a little bit. Oh, man, it's taking a long time. And let's say you leave the room. All right? The next time you come back, your whole kitchen is probably going to be on fire. Okay, and you may burn the whole house down. Now, what? I was just trying to melt the wax. So what happens to hydrocarbons? You melt it to a liquid, and the stove is still on. Now what happens? It changed from a solid to a liquid. Now what's it going to do? Liquid to a gas. You start using vaporized candle, and the vapor comes out. What's going to happen to the vaporized candle? What if it comes down where the flame is? You'll have a huge fireball. Huge. The double boiler simply means I have a pan within a pan. I heat this out here. That's what's in contact with the flame, but the other thing is not. Now, I don't think you understand how dangerous this is. Do you know that you put gasoline in the car, but what form of gasoline does a car actually use? You say, what do you mean? The stuff I put in there. That's not true. So you have a little fuel pump, and it pumps fuel from the tank up to the engine, doesn't it? Then what? What's it do with that liquid gasoline? Does anybody know? Say it again. Yes, but before, they don't actually put liquid, they don't want to put liquid gas in there. They vaporize it. So it goes through this thing called a carburetor. A carburetor makes it come out as a fine mist, and it mixes with air. So you have air mixed with vaporized gasoline. And that's what explodes. That's what explodes in the piston. Got that? A very dangerous thing. How many of you have a barbecue grill that you have to actually light? I mean, you have to, charcoal lighter. Anybody do that? Or you guys all have gas grills or something? You use grills? Okay, well, a charcoal grill, you can get the expensive charcoal that already has hydrocarbons soaked in it, and you just throw the match down and it gets ready, right? But if you don't, you usually have to buy this charcoal lighter fluid. And so you put it on there and you light it, and a lot of times the fluid burns, but the charcoals never get hot enough. So here's a mistake people make. They'll put some more charcoal fluid on there, and all of a sudden they'll see this great big cloud. It looks like smoke. And then they're going to light it. Well, what happens? And they get like this. What happens? See, the charcoal's down here, but the cloud is right here. And the part you can't even see is right here. So what happens when they try to light it? It ignites. It's the vaporized charcoal lighter fluid, isn't it? All right. Okay, now, I want to talk about this over here again. This said that stearin is going to, what else did it say stearin was good for? It said here, raise the melting point, and what else? Prevent the candle from burning too fast. Church candles are often pure stearin. What? What's that all about? Why would they do that? Has anybody gone to a church where they have a lot of candles? You do? Okay, you probably never ask them. That'd be something to ask them. Where do you get your candles? What are they made of? But why would a church want to have stearin candles? Yes?
Because they sit up there and they burn for hours.
They do. And you don't have to change them as often, do you? Well, pretty nice.
So many of them.
And there are a lot of them, aren't there? So, see, now it makes sense. I had a student, and I'll tell you her name because she graduated many years ago, but she's actually came back and helped the volleyball team, and her name is Lauren Buss. And do you know Lauren Buss? Really?
Yeah.
She may not like it that I use her name every year, but here's a 10th grader, just like you. And when she read this part of the article, a little light bulb came off. She said, wait a minute, my mom and I do this thing at home where we take bottles. Now they have like wine bottles or some other kind of bottles. And, oh, by the way, on your elements things, I need those back. So can you go ahead and pass those down? Pass down, Dave, when you get them, put them on that middle table, okay? Do it face down. Nobody else needs to see what you got. Yeah, you don't get to keep those, sorry. So
That didn't work.
a little light bulb went off, and she said, wait a minute, my mom and I do this project, and we go to the hobby store, and we purposely buy these special kind of candles. And I'll show you what they look like in a minute. And what you do is you find a bottle, and you put it on there, light it. And right away, it starts melting. It melts pretty fast, and it starts dripping all over the place. Now, the next thing you do, you break that off, or you put another kind of candle there, and make it drip here. And it makes a really beautiful looking bottle. You probably don't think a bottle could look beautiful, but with wax melted over it, it looks really nice. If I owned an Italian restaurant, I'd do that. It just looks Italian, okay? Whoops, okay. So anyway, this is what I call real extra credit. She looks at the box, she finds the name of the company, she looks it up on the internet, she writes a letter to the company and says, we're doing a project in here, and I notice your candles melt very fast, and we talked about stearin, and that makes it slow down and doesn't burn as fast. Do you guys use stearin at all? And the president of the company, I'm not saying it's a huge company, but the president of the company writes her a letter, I still have that letter, writes her a letter and saying, that is very observant of you, and I'm going to tell you about it. You're right. You are correctly right. We use this kind of paraffin, and we do not put any stearin in there because we do want them to melt fast. And she go ahead and asked her some more. I told her some more things, and not only did she thank her for her thing, but she sent her three boxes of these candles, and I'll show you what they look like. I might even burn one tomorrow. But they look like this. Notice how what do you think's going to happen there? See how it's slanted? What do you think's going to happen? It's going to start dripping right away, doesn't it? And it melts quickly, and it drips really well. And it's for art. It's called Dripstick. And anyway, I thought that was some really good extra credit. And it came from her saying, wait a minute, we do this. And it just something came up in her head and said, we do something like this. I do an art project like that. All right. Now, I do want to mention a couple other things. Notice that it said if there is a fire made with any kind of hydrocarbon, why do you not want to put water on it? If I had a gasoline fire, why don't I just pour water on it to put it out? If I have a paraffin fire, why don't I just throw water on it? What do you think?
The fire will grow now.
It'll what now?
It'll like expand.
Will it? Why?
Oxygen in the water.
Why? Okay, why?
Oxygen in the water.
Say it again.
Oxygen in the water.
That's a good guess, but it takes a lot more than that to break down water to get the oxygen out. So if I took an oil fire and I threw water on it, it would spread the fire all over the room. Why? Yes?
Is it because oil and water don't mix?
They don't. And they have a fancy way of saying that, and the word is soluble or insoluble. You get that? So one thing about hydrocarbons, they do contain carbon and hydrogen, and they're all fuels, they all burn, and all hydrocarbons are insoluble in water. They do not dissolve in water. They do not dissolve. Salt is soluble in water, but gasoline, what? No, I don't care how much you stir it, it's not going to mix. How about vegetable oil? What do you think vegetable oil might be? This doesn't mix with water. What do you think? Libby, what do you think? It might be made out of what? What did we say didn't mix with water? hydrocarbons. So vegetable oil is probably almost all carbon and hydrogen, isn't it? Yes? All right, so that's it's insoluble in water. How many of you tried that? You put some wax in some water. Did you notice it? It didn't mix, did it? Now, did it sink in water or float in water? Did anybody do this? What is it? It did. Not only is it not mixed with water, it's actually less dense than water, isn't it? Less dense. All right, and you got the thing, you understand this right here? All right, let's go a little bit further. Let's go down here to, I need somebody to read the next two paragraphs. Yes, Laura, thank you.
Faraday, whose name is usually associated with his far-reaching work on electricity and magnetism, also did the classical work on the physics and chemistry of candles. In 1860 and 1861, as part of his celebrated Christmas performances for a
Juvenile
auditory at the Royal Institution, he gave 6 lectures designed to show the vast amount of science in a deceivingly simple candle. In trying to understand why a candle burns, I have repeated some of Faraday's experiments, adding a few and investigated current theories of flames. Except for modern theories of molecular and atomic emissions, the
Elucidation.
of the candle flame has progressed surprisingly little since Faraday's time.
Stop for just a minute. Since Faraday's time, with all our modern equipment, we still don't know that much more about the candle than he did, than he discovered. That's pretty amazing. All right, one more paragraph.
Once you light your candle, you will quickly notice that the heat radiated from the flame melts the wax in the wick. The liquid wax is pulled up the wick by capillary attraction, which is to say that the attractive molecular forces between the wax molecules and the wick molecules pull the wax upward. Once the wax climbs to near the top of the wick, it is vaporized. The released hydrocarbon molecules play a variety of roles in the flame.
All right, now, I'm going to double check my time because I'm going to do, if I have time, I'll do a demonstration today. If not, okay, to the one. That's close. We have 4 minutes. I can do it. I think I can do it. All right, so he's going to, if you had to write a story about how a candle works, you might start like down here. It might say, number 1, when you light the wick, what? The heat from the wick does what? What does it say here? The heat from the wick. Leroy, what do you think? It says here the heat from the wick does what?
Melts the wax.
Yes. So we changed the wax from a solid to a liquid. But the flame never touches the solid candle, and it never touches the liquid candle. So now what happens next, Leroy? After I change it to a liquid, what happens?
The liquid is pulled up by the wick, up the wick.
Wow, how does that happen?
Capillary attraction.
Okay, so let me see. I think I have time to do it. I'll show you a quick demonstration. I may do it again tomorrow just because I don't want to rush it, but I have here a, whoops. Oh, here they are. I have these little glass straws. See those? These are called capillary tubes. Capillary tubes. Now, so in order for you to be able to see this, I'm going to put a drop right here of some red food coloring. And then what I'm going to do here is I'm just going to put the end of the straw right here. Okay, now do you see what happened? I didn't suck on the straw, but what happened to the red dye? See how it went up there? Now, why does that happen? Why does it happen? And so talk a little bit of science here. Now, Faraday called it capillary action, or your article calls it capillary attraction. Same thing. Okay, now, this thing called capillarity, that's another thing you could say, is 2 parts. One is adhesion, and one is cohesion. Okay, now, So what we have here is, a long time ago, I always had trouble. Which one is which? Have you ever seen a piece of tape? Does anybody know names of tape? Scotch tape,
Duct tape.
masking tape. What's another word they have?
Duct tape.
Duct tape, or one that sounds like this word. Have you ever heard that? Have you ever heard of adhesive tape? Okay, so adhesive tape is when different materials attract each other. So when I'm saying this, do you think glass attracts water? And it does. It does. I have another one. Watch. See this little piece of tissue? Watch. What's happening there? That is capillary attraction, and it's made of two parts. I need to stop. Remind me that I just barely got, sorry, okay, I can do these again.